Continuing now with example 7 from the section 9.2 notes. We're finding some matrix products. We've done A times B. Let's do now B times A. We're going to list the 2 by 2 matrices side by side, but first we're going to write B. Then we're going to write A. So in an opposite order. Okay, and here again there's going to be 4 entries total. I'll leave some blanks here. And let me label row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2. So to get the first entry, we multiply entries in row 1 of column B by entries in column 1. I hope I said that right. Let me try again. We multiply entries in row 1 of matrix B with column 1 of matrix A. I think I've been saying column in place of matrix sometimes. I apologize if I have misspoke. So row 1 with column 1, that would be, I'll show the actual entries, 3 times 1 plus 2 times minus 2. Row 1 with column 2, 3 times 2 plus 2 times 3. Row 2 with column 1, 1 times 1 plus minus 1 times minus 2, and row 2 with column 2, 1 times 2 plus minus 1 times 3. Adding, multiplying and adding, 3 plus negative 4, negative 1. 6 plus 6 is 12. 1 plus 2 is 3. And 2 plus minus 3 is minus 1. All right. Well, what do we see? A times B is not equal to B times A. The results have the same order, but different entries. So what we see is that matrix multiplication is not commutative like multiplication with real numbers. If you change the order, you may get a different outcome, or it may not even be possible to compute the product at all. That will be demonstrated here in a moment. Let's do A times C. Okay, A times C. Okay, A is the 2 by 2 matrix 1, 2, negative 2, 3. C is the 2 by 3 matrix 4, 0, 1, 2, negative 2, 3. A has order 2 by 2. C has order 2 by 3. Notice the inner numbers here match, meaning this product is defined. The outer numbers determine the order of the resulting matrix, which is, like matrix C, 2 by 3. So what we're going to have here are 6 entries with 2 rows and 3 columns. 1, 2, 3, 4, 5, 6. Once again, I'll do some labeling. This is row 1, column 1, row 1, column 2, row 1, column 3, row 2, column 1, row 2, column 2, row 2, column 3. So now we're going to take entries from the from rows of A with entries from corresponding columns of C. So row 1 of A times column 1 of C would be 1 times 4, which is 4, plus 2 times 2, which is also 4. I'm just going to show the products and just add them and not show quite as many details now. Row 1 of A with column 2 of C. That would be 1 times 0 is 0. And 2 times minus 2, minus 4. And then row 1 of A with column 3 of C. 1 times 1 is 1. And 2 times 3 is 6. Isn't matrix multiplication fun? Row 2 of A with column 1 of matrix C. Negative 2 times 4 is negative 8. And 3 times 2 is 6. You've always got to have entries that correspond, the same number of entries in a row as in a column. Row 2 with column 2. Negative 2 times 0 is 0. 3 times negative 2 is negative 6. And row 2 of A with column 3 of C. Negative 2 times 1 is negative 2. And 3 times 3 is 9. And then your wonderful instructor hopes he hasn't made any dumb mistakes. 4 plus 4 is 8. 0 plus negative 4 is negative 4. 1 plus 6 is 7. Negative 8 plus 6 is negative 2. 0 plus negative 6 is negative 6. And negative 2 plus 9 is 7. Finally, what about C times A? Well, C has order 2 by 3, 2 rows and 3 columns, and A has order 2 by 2. Now previously we did A times C. Now we're doing C times A. If I list them in this order and I look at the inner numbers, the number of columns in C and the number of rows of A do not match. If those don't match, the product is not defined. CA is undefined. So it was possible to do A times C, but it's not possible to do C times A. Again, matrix multiplication is a little bit peculiar, but it is useful. It is useful even though it doesn't work the way you would expect it to work. So one of the things that we have to get used to is the fact that changing the order generally changes the outcome, and in some cases even makes it impossible to perform the matrix multiplication. So before moving to the next example, we just note that matrix multiplication is not commutative. That is, for two matrices A and B, it's generally not true that AB equals BA. There are exceptions, but usually changing the order changes the outcome. Now continuing to example 8. A is a 2 by 3 matrix, B is a 3 by 2 matrix. Find, if possible, A times B and B times A. Let's first of all list the matrices in the order we want to multiply them, and along with their orders. A is a 2 by 3 matrix. B, a 3 by 2 matrix. Notice these inner numbers match, so the product is possible, and the outer numbers determine the order. So the order of A times B should be 2 by 2. That is a square matrix with an order different from the two matrices that are being multiplied. So the order has to be just so to be able to do the multiplication, and the resulting order of the product may not be what you would expect. Okay, to actually perform the multiplication, A times B, as before, strongly recommend you just write the matrices, being careful to copy them down accurately, side by side, so that you can pair rows and columns. Now, the order of the product tells us how many entries to expect. In this case, we should expect 1, 2, 3, 4 entries. It should be a 2 by 2 matrix. We're going to take row entries from A and column entries from B. We have row 1, column 1, row 1, column 2, row 2, column 1, and row 2, column 2. Okay, pairing and multiplying and adding as we go. Here we go. So row 1 of A with column 1 of B, 2 times 4 is 8. Negative 2 times 2 is negative 4, so plus negative 4. And 1 times 3 is 3. Row 1 with column 2. 2 times negative 4 is negative 8. Negative 2 times 0 is 0. 1 times 1 is 1. Row 2 with column 1. Negative 1 times 4 is negative 4. 3 times 2 is 6. 0 times 3 is 0. Row 2 with column 2. Negative 1 times negative 4 is 4. 3 times 0 is 0. And 0 times 1 is also 0. Simplifying, we obtain 8 plus negative 4 plus 3 is 7. Negative 8 plus 1, whoops. Negative 8 plus 1 is negative 7. Negative 4 plus 6 plus 0 is 2. 4 plus 0 plus 0 is 4. So having done A times B, let's try B times A. B is 3 by 2. A is 2 by 3. The inner numbers agree. The outer numbers therefore tell us the order of the product. B times A would be order 3 by 3. So in this case, when you change the order, you can still do the multiplication, but you get a larger matrix. You get a 3 by 3 matrix rather than a 2 by 2. Again, this is par for the course when it comes to multiplying matrices. Here again, what we should do in computing B times A is list the matrices side by side, but this time we first list list B, and then we list A. All right, in this case, B times A is 3 by 3, so there's going to be 9 entries. Here we are. 1, 2, 3, 4, 5, 6, 7, 8, 9. You don't have to do this yourself. I'm just trying to demonstrate how it works. I don't know if I'm doing a good job of it or not, but I'm trying. So you have row 1, column 1, row 1, column 2, row 1, column 3, etc., etc. I'm not going to label them all. Too time consuming. But we take, I'll try to indicate what we would get. Hopefully you can follow along yourself. So row 1 with column 1, 8 plus 4. Row 1 with column 2, negative 8 plus negative 12. Row 1 with column 3, 4 plus 0. Row 2 with column 1, 4 plus 0. Excuse me. Boy, I'm almost out of time. 4 plus 0. Row 2 with column 2, negative 4 plus 0. Row 2 with column 3, 2 plus 0. I'll pause and fill in the rest of them since I'm almost out of time. So I finished it up. I did the last row and then I added the numbers, and you can see the 3 by 3 matrix that results. So we'll continue the notes in the next video.